Hello everyone, in this video I'm going to be talking about how to nitrate the benzene, or another way of saying how to do nitration of an aromatic compound. So I have a simple example here where I got a benzene reacting with HNO3 and I have the H2SO4. So your final products, and I'll tell you how that really works, but to begin with, your final product is going to have a nitro group attached on the ring. Now, right now, it doesn't really matter where the nitro group goes because there's nothing else attached on the aromatic ring in this particular case. If you already have some substituents attached on the ring, then you got to worry about whether you're going to put it on the ortho, meta, or para positions. And I'll have some examples in a little bit. But right now, I want to talk about the mechanism of this because it's fairly important. Like I said, these are your electrophilic aromatic substitution reactions. So that means it's the electrophile that's going to be substituting a hydrogen on the ring. So the very first thing you need to figure out is what's going to be your electrophile in every single one of those reactions. So I have this nitric acid. So if I go ahead and draw the nitric acid, this is how it's going to look like. So minus charge here, plus charge here. And then I'm reacting that with H2SO4. So sulfuric acid is acting as your catalyst here to just make sure you have your electrophile made. So sulfuric acid is indeed a stronger acid than the nitric acid. So nitric acid is going to act as a base here. So I want to go ahead and protonate this oxygen here in the first step. So I use this to protonate that oxygen, and I make this HSO4 1 minus as my conjugate base here. So I'm going to go ahead and copy this down and just put it right here. And then the process, I have protonated this oxygen atom, so I got a positive charge. Plus, I got HSO4 1 minus made that I'm going to be using in a little bit. And then in the second step, you have this conjugate acid made out of that nitric acid, but now this has a good leaving group. So first reaction, you can write that in an equilibrium because it's just an acid-base reaction. And the second step, I can have this coming in there, the lone pair on the oxygen coming in there to create the double bond, and in the process, that's going to kick out this nitrogen-oxygen bond, making water to leave, and then that leaves you with this nitro group with nitrogen having your positive charge. So this is going to be your electrophile in this particular case. So once you know what your electrophile is, you can use your ring to do the attack. So let me just go ahead and copy this down here. And then I have this nitro group here. In the first step, I'm going to be using one of the pi bonds in the ring to do this nucleophilic attack from the ring. And then the pi bond between the nitrogen and oxygen breaks. And then that makes it, so I'll kill that pi bond. So I'll call this 1 and 2. Now between 1 and 2, it doesn't really matter which particular carbon the nitro group goes to because right now it's symmetrical. So I'm going to go ahead and put a nitro group here. Positive charge here and a negative charge here. And that I already had a hydrogen there, so make sure you keep that in mind. And you can change the color there so you can see the color coordination. So I already had a hydrogen there. I already had a hydrogen at number 1. But this carbon 1, before I had a 4 bonds, now has 3 bonds. It becomes electron deficient, so I'm going to have a positive charge there. And then you can have these resonances drawn. So I can go ahead and draw this coming down here. It comes down here, and then I'm going to go ahead and take that hydrogen away, actually. So you get a double bond here, positive charge here. Then I'll have another resonance structure where this can move down here. So when this moves down here, I get a positive charge here. Okay, so these are your three resonance structures that you have drawn. And then this is usually your rate determining step because you're killing the aromaticity of this benzene ring. But then the last step is going to be the fast step because you are reforming or regaining your aromaticity. So finally, your last step is going to be having the conjugate base, which you have created in the beginning, HSO4 1 minus, is going to be coming in, grabbing this proton here. When that grabs that proton, this actually goes in there to create the double bond. So when this creates a double bond, I'm just going to go and copy this down here. You have the nitro group installed on it. So you lose an hydrogen, and then you got the nitro group attached, and you can just write down NO2 there as well. And your side product is obviously going to be the hydrogen that was came in here, and then you have the HSO4 1 minus, so you will be retrieving your sulfuric acid because it's in a catalyst, so you must retrieve that at the end of the day as well. So your technically the side product was water, if you think about it, but then sulfuric acid was regained back. So this is how you do the mechanism of nitration of benzene. Even if you have substituents attached to it, you just have to worry about whether in the presence of substituents, whether a nitro group will be attached on the ortho, a meta, and a para position, and then do the mechanism just like you have done the mechanism here. So let's do some examples here, and I have some of these um, benzene aromatic rings, and I already have some substituents attached to it. So I got to worry about whether this is going to be an ortho, para, or a meta attack. So let's look at this first one. I got a ethyl group. This is an electron donating group, even though it's a mild, or you can say it's a weak electron donating group, but still an electron donating group. So I'm gonna have the attack either at the ortho positions. Those are your ortho positions. This is your meta position with respect to that ethyl group, and this is your para position. So since it's an electron donating group, we know the electron donating groups or the activators do ortho and para substitution. So I'm gonna have two possible products there. I'm gonna have, just gonna copy this down here, and I'll just take out everything here. Either I can have a nitro group on here, and I can have a nitro group on the para position. Now, obviously, we know that there are two ortho positions and one para position, so you have twice the probability of having the nitro group on the ortho position than the para position, and it's easily true if you have a relatively smaller group as in a substituent, but if you have a bigger group, then your steric factor becomes dominant, and you try to put the nitro group where you have the least steric hindrance. Now, if I want to compare ortho versus para, obviously ortho being right next to this ethyl group is going to be sterically hindered, and as a result, nitro group will be less likely to be attacking to the ortho position, but rather it's going to be attacking to the para position in that particular case. So this is going to be your major product, and this is going to be your relatively minor product in that particular case. So a lot of time they ask you to figure out, draw the major product, and if you're asked to draw only one product, you're always going to be drawing the major, and you can ignore the minor product. Let's look at this next one. Still doing the nitration, but I got two groups on it now. I still have an ethyl group, so I know this is in a weak electron donating group. And then I got an OH, which I know it's going to be a strong electron donating group. So when you have the same type of groups, like two electron donating groups, the question is going to be, who do I really listen to for this incoming nitro group? And then the answer is going to be you listen to the stronger one, or another way of saying the stronger group is going to dominate in that particular case. So I want to go ahead and put this nitro group ortho or para with respect to the OH. So then your ortho positions are actually going to be, so with respect to OH, this is going to be ortho, this is going to be ortho, and this is going to be your para. But then if I look at, suppose, change the color there. If I look at the ethyl group, with respect to the ethyl group, this is going to be your ortho, that's going to be your ortho, and this is going to be your para. So it does kind of falls in the same. There's like an additive effect where the ortho and para positions are actually going to be falling in common when it comes down to both of those electron donating groups. So it actually does help it and just makes the ring even more reactive. But now between those, where do I really attack? And the question is going to be um, either I can attack, let's say, attack here. That's one possibility, or I can attack here. This other position right now, this is too sterically hindered. So I'll say too crowded for this nitro group to come in there. So as a result, either I'm going to be attaching there or attaching there. And even among those two other positions I have left out with, if I have to pick one out of those two, I would pick the one that's right next to the OH because OH is going to be a relatively smaller group than the alpha group, and as a result, your nitro group is going to go to the place where it's least sterically hindered. So I'm going to go ahead and make my major product. Just copy this down. So let's take this out here. So major product is going to be having the NO2 group here. So I'll say this is going to be least sterically hindered. Okay. What if you have an electron withdrawing group? So this next example, I have an electron withdrawing group is the mild electron withdrawing group because got an carbonyl carbon directly attached to the ring. So I know the electron withdrawing groups are going to be placing this NO2 group meta to with respect to that. So these are your orthos and these are going to be your meta and this is going to be your para. So since I know this is going to be meta director, I'm just going to go ahead and put this nitro group right here. So when it comes down to making the mechanism, it's going to be very similar. If you understand the mechanism on that, you just do the attack on the meta, figure out where the positive charge is going to be, and then draw the resonances and eventually get rid of the positive charge by removing the proton, restoring the aromaticity by using the conjugate base of your sulfuric acid. What if you have both electron donating and electron withdrawing groups present? So this is your electron donating group and this is your electron withdrawing group. So that does happen a lot of time. And in that case, you're going to be listening to the stronger one. You're always going to be listening to the electron donating group. And since I'm going to be listening to my electron donating group, this is going to be the ortho, well, and this is going to be the para. So um, because this so where would it go? I can't really have it here. I can't have it here because it's too sterically hindered. Um, and then I can have it either at the para or the other ortho position, but then I gotta look for who is least sterically hindered, and I would say this is gonna be your least sterically hindered. And since this is the least sterically hindered, I'll have the nitro group attached right here, so I can go ahead and write that down like this. So this is how you're going to be doing the nitration, and I got multiple examples where you have already substituents present on the ring. Um, and once you understand this, they're going to help you later on once you start doing the synthesis problem on the aromatics. If you have any questions, feel free to leave any comments in the section below.